All right, so far we know how to get started to set up the initial Tableau. And if I give you a Tableau, you would know how to transform it into a point for your region. In this video, I want to teach you how to go from one Tableau to the next to get to the optimal corner. All right, so the simplex method will use these Tableau to follow the boundary of the allowable region from one corner to the next until it reaches the maximal value for P. Here is how to obtain that maximum value. If there are negative entries in the last row, so that's the objective function row, so that's the row that corresponds to the function that we're trying to maximize, then you're not at an optimal solution. If there are no negative entries in the last row, then you are, and you can stop. All right, so if there are negative entries, then you need to pivot. You identify the pivot P by taking the intersection of the column with the most negative entry in the last row and the row with the smallest positive ratio of entry in the last column and entry in this most negative column. All right, so you look at all these ratios and you find the one that's smallest and positive. And just know if there are no positive finite ratio, then you stop. That means the problem has no optimal solution. All right, so you want to pivot on that element you found. The first thing you do is you turn that pivot into a 1 by multiplying by, well, if it's P, then you multiply by 1 over P. And then you want to clean up that column so that it looks like it's a basic variable. So you perform elementary row operation using the pivot, and you're only allowed to use the pivot, otherwise you'll mess up the other columns, to zero out the rest of the entries in the pivot column. If negative entries remain in the last row, then you return to A and you keep going and you do A again and again and again until there are no negative entries, and then you can finally stop. All right, so let's try this. We'll apply it to our favorite example. Let's say we want to maximize 2x plus y under the usual restrictions. We've already set up the initial Tableau, so let's maximize P using the simplex method. And the starting Tableau is this. All right, so let's apply the method to this. We have negative entries in the bottom row. We have the -2 and the -1, and so we know we're not at an optimal solution. So now I must identify the pivot. I'm going to look at the most negative entry. So most negative entry, that's the -2. So that's going to be one of the columns that we consider. Well, the columns that we consider. And then we're going to look at the ratios for each of the rows. So the entry in the last column, that's going to be 10, divided by the entry in the orange column, in the most negative column, that's going to be 0. That's infinity, so that's not going to be possible. Here, the ratio is 15 over 1. That's 15. That would be good. And then the next ratio is 36 divided by 4. So 36 divided by 4, that's 9. So this one is the smallest positive. And so that's the column we want. The intersection, the 4 is our pivot. All right, so we want to pivot on that one. That means I'm going to start by dividing that row by 4. So let me move this so I can write it here, up. All right, so I'm going to take row 3 divided by 4. So first row doesn't change, 0, 1, 1, 0, 0, 0, 10. And then I have 1, 1, 0, 1, 0, 0, 15. Now I'm going to divide that one by 4, so I'll get 1, 1/4, 0, 0, 1/4, 0, 9, and then I don't touch the bottom row, at least not yet. So -2, -1, 0, 0, 0, 1, 0. All right, so here's my pivot, and I'm going to clean up the whole column to get 0 above and get 0 below. So that means I need to take row 2 minus row 3. You have to use row 3, no other possibility. I'm going to take row 4 plus 2 row 3 to get rid of the -2. I'm going to get 0, 1, 1, 0, 0, 0, 10. All right, so I'm going to subtract row 3, so that's going to give me 0, 3/4, 0, 1, -1/4, 0, 6. This one I don't touch. And then the bottom one, 0, -1 plus 1/2. That's going to give me 1 -1/2. 0, 0 plus 2 times 1/4, 1/2. 1 plus 2 times 9, 18. All right, so I've pivoted once. And at this point, you start again. You start by asking, is there a negative entry in the bottom row? Let me shrink that a tiny bit so I can write underneath it. All right, is there a negative entry in the bottom row? Yes, there's only one, so that's the one we're going to use. There's the -1/2 right here. That means you're not done. That means you have to pivot again. Now you need to look at the ratios again. So let's look at the ratios here. Always the constant divided by your most negative column. So this one would give you 10. Here, I would have 6 over 3/4. That's 2 times 4, that's 8. And this one, the ratio will be 9 over 4th. That would be 36, which is way too big. We take the smallest one, so the smallest one is 8. So smallest positive is 8. That's going to be my row, and I have the intersection right here. So my pivot this time is this 3/4. And so first operation I need to do is to make that one a 1. So row 2 divided by 3/4 into row 2. That's going to give you 0, 1. Doesn't change the first. Second, I'll get 4/3. I'll get minus. So divided by, so that's times 4, so that's -1/3. 0, 8. And then the other one hasn't changed yet. And the bottom row doesn't change either. All right, so we're halfway through our pivot. Now we need to clean the column using that one. So I'm going to get rid of the 1 on top, the 1/4, and the -1/2 by using row operations. I need to use my pivot entry to do this. So the operations I'll need are going to be row 1 minus row 2 into row 1. I'm going to take row 3 minus a quarter of row 2 into row 3, and row 4 plus a half row 2 into row 4. All right, so please take your time when you're adding and subtracting fractions. So here I'm just subtracting 1, that's okay, minus a 4/3, 1/3, 0. 10 minus 8 is 2. Notice that my constants always stay positive, and that's why we make these choices here, is to make sure that we take the one that would move us to the nearest value so that the other remaining ones are positive. So here I had 10 and 8, and what I get is 8 here, and then the difference between the two here. As long as we take the smallest, that difference will be positive. All right, this row was our pivot, so we don't need to change anything about it. Now the next row, we take minus a fourth. So far it's easy. Minus a fourth, that's minus a third. All right, so this one, let me compute it on the side. It looks complicated. I get a fourth minus a fourth times minus a third. That's going to be on 12, so 312 plus 1 on 12. That's 412. All right, so we get a third. 9 minus a fourth of 8 minus 2, that's 7. All right, then 0, 0, 0. 4/3 times 1/2, that's 2/3. All right, let's compute this one. That column is harder. So 1/2 plus 1/2 of minus a third, that's 3 minus 1 over 6, and that's 1/3. And then this one stays 1, and then the final one is 18 plus 4, that's 22. All right, so let me erase these. At this point, we have no negative entries, so that makes us happy. So we're at the optimal solution. And at this point, we can read what that optimal solution is. These are our basic variables. I have x, y, s1, s2, s3, p. So x is the third. I get the value of x from this one. I get 7. I get the value of y from this one, because that's where the 1 is in the y column. So I get y equals 8. S1 is 2. That's from the top column. And the last one is p. P is 22. And the non-basic is S2 and S3, which are equal to 0. All right, let me shrink this a tiny bit so I can add my conclusion. So here the conclusion is P is maximum at x equals 7 and y equals 8, where P is 22. Excellent. That's the same thing we had found graphically. Let's go back to make sure. Where was it? Here, perfect. P is 22 when x is 7 and y equals 8. That's the maximum value. That's what we found graphically, and that's what we're finding using this method. That's a good sign. To show you what the method is doing, let's answer B. Here are the tableaus obtained after pivoting in A. Place the corresponding point in the allowable region. All right, so two of them we've already done. This one, if you remember, was the initial tableau. We looked at it last time, but let's do it again. All of these are assigned the values 10, 15, 36, and 0, but x is basic, and so that, is non-basic, and so we get 0, and y is non-basic too, and so we get 0. So the starting point is the origin, and that's usually the starting point for all of these. Now in the middle, right here, I get that x is basic, and so x is 9. And I get that y is non-basic, and so it's 0. Let me write it that way. I don't like the equal basic. So this x is equal to 0 because it's non-basic. Y is equal to 0 because it's non-basic. All right, so that's the first point. Second one, y is non-basic, but x is basic, and it's equal to 9. So the second point is 9, 0. So the first pivot moved us in the x direction to the nearest corner, nearest vertex. Now, when we pivoted a second time, we made x and y are now basic. So the value of x is given by the third row was 7. It's basic. And y is 8. It's basic too. And so we're right here as 7, 8. And so really what the simplex method is every time you pivot, you move to the next corner of your region until you've hit one where if you moved further, you would decrease the value of p, and that means that the optimal solution is there.